Morning and welcome to Physical Science in the AM. I'm Joel Shandelka. Hot dog, it's a terrible hot day in this classroom. We're going to take a look at something called Hess's Law. You guys got this in front of you. It's the energy involved. It's a technique to find the energy involved in a reaction. The first thing we have to understand, though, when we do Hess's Law is heats of formation. And I have a formula up there, delta H, which means the enthalpy or the heat energy change, with a little f on it. That's for formation. It's the heat energy of the product minus the heat energy of the reactants. But we're not going to do it that way. We're not going to subtract. We're just going to be given heats of formation from a table, so the subtraction's already done. What is a heat of formation? It's the loss or gain in energy when 1 mole of a substance is formed from its elements in their standard state. So it's important we understand which elements comes as a group of 2. There's 7 of them. Remember, start at 7, nitrogen, make is 7. That's nitrogen, oxygen, fluorine, and so on. And the 7th one is hydrogen. Those come as groups of 2. Pretty well everything else are singles. If I say iron, it's just F. Okay, just a second here, I'll pause and update something. And one thing is you'll look up stuff and you'll say, oh, oxygen isn't on this table. Why not? Well, it's in blue. Any element in its standard state has a heat of formation equal to 0. So right there I got, for example, you won't find those on the table because it's an element. For oxygen, the heat of formation is 0. We just assume that's the base level sort of change in energy. Now, we're going to just practice writing the formation equation for carbon monoxide and carbon dioxide, and we're going to, well, we'll take a look. Learn to do by doing. So the first one, the heat formation for CO2, I give you a value. Let's write out the formation equation. What are the elements that form carbon dioxide? The words are carbon and oxygen, right? We just have to know if they come as singles or groups of 2. I hope we know this. We have carbon plus an oxygen forming CO2. That's the formation equation. Then we have to make sure it's balanced. Come on up here then and grab. In this case, it actually is balanced. It's not just balanced overall, it has to be 1 mole of the substance that forms. Balanced, and it is for 1 mole CO2. You'll see. Anyways, this first one didn't require anything. So we're going to just write down this beside it. Delta H down. Just rewriting the information here. That's how many kilojoules are forming a mole of CO2. Okay? That particular reaction. Now the next one's going to have a little monkey wrench. Same elements, but balance comes out there. Grab that sheet right. So once again, carbon monoxide, well, it's still carbon plus oxygen. Here's where it gets tricky. Oh, not that tricky, but it involves fractions. This is why the other day we were practicing balancing all the fractions. You have to keep it on the right-hand side as 1 mole for this number to be accurate. 1 mole of the substance formed. So I'm going to just sort of cement in a 1 here. I don't mean to write it, but I'm just getting it clear. That can't change. So it's only the left that we can balance. When I look at it, I'm going to put them in red just to emphasize. This is 1 carbon to 1 carbon on the right. That's good. But we have O2, we only want a single carbon. We have to use a fraction in this case. The fraction then get multiplied 2 by to get 1O. saying is this. This is why we're playing around with fractions to balance. This means 1/2 of O2, that's a single O. Now it balances. Why did we do that? Because a formation equation must be for 1 mole of whatever you're forming. Okay? Once you've done that, this delta H value is true. This is particular only to carbon monoxide. Okay? Well, take a look at something further, but before we do, I'll pause and update the text. So flipping the page. I have a chart here. Heat of formation. Once again, a reminder, the heat of formation of an element is 0 kilojoules per mole. Everything else, there's a value for. This is obviously not all the compounds in the world, but these are the ones we'll probably use on these problems. On a test, I'd give you these values as you need them. You can always Google them up too, but you won't need to in my classroom. You'll notice that I wrote one thing down. Fine. This is propane, C3H8. For the gas, it's negative 104.7. You form liquid propane in different environment pressures. It's negative 103.8. It's slightly different. And that's just it's because it comes up in a propane. Okay? Actually, I eliminated isoprene as gas. Okay. Using this chart, so it's fairly simple. Calculate the delta H, the enthalpy change, of the following reaction using formation. We use this formula for it. The sum of is, as soon as I'm mathemizing for it, capital sigma means add up, sum. Sum of the delta H values for products, that's one here. Minus, and then I have this bracket here for a reason. You've got to add them up before you subtract. The sum of, added up, all of the reactants. Most things when you find a change. The final thing minus the initial. You reach your odometer after going on a trip. You want to know how far you went. You program something. You just go final odometer reading minus the initial odometer. Final minus initial. Okay. So, see, I've prompted you with blanks here. We have to balance this. There we go. So let's try this out. Okay, C3H8. I'm going to do it, and I may be erasing, but I'll pretend I don't know what I'm doing. I pretend I don't have the answer. So, I'm thinking 3 carbons on the left. I might need 3 CO2s. I think I might erase it, so I'll put it in lightly if I was doing it. Now, when I do that, I need 8 hydrogens. So I need 4 here. Okay, I've got carbon and hydrogen balanced. Let's see about the oxygens. On the right-hand side, I have 3 times 2, so 6 plus 4. I can do this one, right? I don't have to erase it. But now I'm going to double check everything. Now, the arrows aren't necessary, they're my fingers. Okay, so 3 carbons, 3 carbons. 8 hydrogens, 4 times 2 is 8 hydrogens. Check. 10 oxygens, oxygens plus 4 oxygens. This does balance. And here's why we need it. Well, we need it balance. You've got to use that with this delta H equation. It gets pretty big, so I'm going to do the products first. And I'm going to get rid of this. So the products are CO2 gas. Look up this. We've got 3 of them. I'm going to put the 3 down right now. 3 times the energy for CO2. I see that up here. Negative 393.5. We have it up here. Now, you'll notice I put a 3 in front because of the balance number in front of CO2. That value of 393.5 that's negative, only for 1 mole. And then I'm going to add that because it said sum of the products. Water, gas. So notice water, I have liquid and gas there, so you got to choose the right one. So the balance number in front of it is 4. H2O gas is negative 242. There's something for you to just show it up. That is all of the products. Now, the reactants. I'm going to put a minus sign in there. Start a big fat square bracket. Add up the reactants. I have one group of C3H8. And I changed the gas until I typed over the original. Negative 104.7. So I'm going to just put that in there as negative 104.7. I don't need to say times 1. Plus 5 groups of oxygen. I look up oxygen on here. I can't find it. Why not? Let's say at the very top. Oxygen. It's an element. And it's 0. But I really don't. I'm going to show it. 5 times 0. Right? Any element. 0. So that makes things easy calculation. Now what? Well, this is just a calculator issue. I'll do it in chunks. You can do it all in one step. Sometimes people make mistakes. I'll do it in chunks. 3 times negative 393.1. Now, 4 times negative 242. I'm going to put that as, instead of adding negative 968, I'm going to just put it as minus 960. Now this one, there's no arithmetic to really do in the second bracket. It's minus negative 104.7 kilojoules. I'm going to make sense out of that. Let's say minus and negative is actually added. 104.7. If you wish to put that whole line into your calculator code, now I'm going to just do the original. Okay? Negative 1180.5 subtract 968 plus 104.7. That means that balanced reaction, propane burning, for 1 mole of propane will give off potentially 2,043 decimal kilojoules of energy by burning. will, when you try these problems, answers are given, products times reactants. Do the arithmetic, figure it out, right? Grab that onto my line. Okay. This happens to be balanced already, so the balancing is done. All you have to do is just 2 times the value of CO2, or, those kind of things. Products times reactants. So you actually start to that out. Okay? Try these. Some on the second page. 5 of them for you to try. Well, let's go with it. The answers are all there, so you know what to do. Okay, let's see here. Okay, I'm assuming people have asked if they needed help. It was usually a calculator issue more than anything. The answers are all given, so you know if you're doing them right. And they seemed okay. If you haven't done all 5, take some time to do them. You need to know how to do this. We're going to take one look at this example, and then we've got more for tomorrow. But this is called Hess's law, and actually we've already been introduced to one form of Hess's law using formation equations, formation energies, heats of formation. Now, in this one here, we're using this information a little differently, and this is what we're going to concentrate on for the next couple of classes. Find the heat of formation of methane given this information. Now, first of all, you got to know what methane is already. So, methane is CH4. Okay? Given this information. Now, we're given this equation here. I'm going to just copy and paste it after a second. But we're also given that the water's heat of formation and the carbon dioxide heat of formation are those values as well. What we need to do first is write out those formation equations. Okay? And we're going to write them out, for 1 mole of water and 1 mole of carbon dioxide. So, water, I'm going to do that one first, is H2 plus O2. Those are the elements that form water. Then I've got to balance it for 1 group of water. I have 1 mole of water because it's formation. So when I do that, H2 is perfect. I need half of an O2. We're going to balance with fractions. That's why I've got you guys a little bit used to working with fractions. And put down the HF, the formation value over here. I'm going to write out the formation equation for CO2 for 1 mole of CO2 and balance it out. It just so happens we've done this before. That carbon plus oxygen is balanced when it forms CO2, so nothing to do. Okay? And I was given this information here. The blue stuff, I'm going to write that out again just so it's all in one chunk. I'll write it in red just because that's the color I've been doing. CH4 gas. CO2. CO2. Water. Okay. That's the given information. I've just rewritten it down in the form that we're going to be able to use. I'm going to do it in a different color here. what our target equation is. Find the heat formation of methane. That's our target equation. When I say target, that's where we want to find the information. So, carbon plus oxygen, or not oxygen, hydrogen. Forming, oh, not arrow, CH4. I've got to balance this, and I just need 2 in front of the hydrogen. That's balanced. Now, put this in a different color because and I call it a target. That's the one we want information about, and no, we can't look it up on the table. I want to see the word. This is what we're learning. That's the new skill. Here's how we go about doing it. We have 3 given equations, given information. 3 questions right now. I'm not going to erase anything. I'll pause and let you guys catch up. Right. Coming back to this, the only reason why I'm calling this our target is because we're asked to find information about the formation. That's this. Okay. So what we have to do is, I'll do this in blue, is we've got to figure out what's unique to the first water equation that appears in here. When I say unique, if there's something in this equation that doesn't appear in the others, I see it's hydrogen. See how hydrogen's in this, it's not in the second or the third red list of equations. I'm going to use that hydrogen to make decisions about what we do. First thing you ask is, we need hydrogen on the left or the right, products or the reactants? Reactants or products. We need it on the left, it's already on the left. So we don't need to flip anything, but we do need to double it. We need to multiply by 2. So what I'm going to just do up here so you know what we're trying times 2. Put times 2 there. We'll do it afterwards, but we're going to just declare it. Okay. So we use hydrogen to make decisions about this. Now the second equation. What's unique to the second equation that appears in the target equation? Now look through. You know what? There's a single carbon here, there's a single carbon here, we need that, and there's no carbon in the first or the third. We're going to use carbon to make decisions. You know what we do? Nothing. It's on the left side and we have one of them, that's perfect. So I'm going to just leave that one for now, and then we'll take a look at the next. Now the CH4 does not appear in either of these. So this CH4 is going to appear like that CH4. We need it flipped, right? Say the word flip or reverse. We don't need to multiply. There's one CH4. That's good. So all I'm going to do is write down, I'll put the word REV for reverse. We'll see how this works in a second. We're going to rewrite all 3 of those equations below this target. And we'll see something with it. So the first one, we're going to do the work right now. And we'll do it in blue. Just, you know, it's reworked. Same equations, just manipulated. So I take 2 and multiply 2H2. So plus 1/2 times 2 for the oxygen. 2 times 1/2 is 1 oxygen gas. 2 times water, so 2 waters. And I need to multiply the delta H by 2. I'm going to use the calculator. It's still negative, but 5.8 times 2, negative 570. I'm going to stack these energy values because we're actually going to do some arithmetic with them. I'll leave them on the right. The second one I said don't do anything to it, so I'm going to just put it as carbon plus oxygen, CO2. Rewrite that. Now, I made a minor error on this other one here. I noticed I called this third equation a heat formation. It's actually just a heat of reaction. You bust. There shouldn't be an F on there because it's not a formation. It's not formed from its elements. It doesn't make a mathematical difference. When I reverse that one, that means products and reactants are reversed. I'm going to just put the CO2 on the left. Two waters on the left, arrow, CH4 on the right, two oxygens on the right. The delta H, the entropy, I'm still putting in the F there, a mistake. It's going to be equal to, well, I flipped the sign when I flipped the equation. It's now positive 890.3 kilojoule. I'm going to put like an arithmetic adding line underneath that. I'm going to do the same thing with the reaction. I made sure that I lined up my arrows and it makes something easier in this next step. Here's what it is. We're going to double check. Does this add up to the target equation? If we made decisions correctly, it should. So here's what I mean by adding up. I take a look at hydrogen. Are there any other hydrogens in these three reactions? I look. No, no hydrogen, no hydrogen. Okay, let's just create it. So these two, nothing to cancel out. But then I look at the oxygen. I notice there's an oxygen here, and two oxygens here. I'm going to put some boxes around. So do you notice on the left side there's a grand total of two oxygens, and there's two oxygens here. In mathematics, if you have two x's on the left, two x's on the right, they cancel out, right? It's the same kind of thing here. These two oxygens and these two oxygens, oh, they cancel out. It's just like arithmetic, and that arrow is like an equal sign. Now, you guys follow that logic? Now I'm looking at water here. I've got two waters here. So guess what? They do the same kind of thing. They cancel. I'm going to just make my slash the other direction diagonally. You can tell that the match moves up. Those waters cancel out. Then I go down to the next equation. Carbon, that's the only carbon. There's no other carbons, nothing to do there. But I notice CO2 has a match left and right. So this CO2 and this CO2 cancel. When I do all of that canceling, what am I left with? On the left side, the reactant side, I'm left with two groups of H2. Plus carbon. And that's perfect because that's what I want. This works. Arrow, and there's only CH4 on the right. That's perfect. Now the arithmetic for this is a formation equation, so I'll put it out there, is, and you just do this, negative 571.6, I'll enter it, plus negative 393.5, plus positive 890.3. I get negative 74.8. Hopefully I didn't make
any mistakes. Did I? You know what I did? You know, I did. Hey, I think this is correct. It's perfect timing. That was just right. We're going to work on these things tomorrow.